Application security, or AppSec, protects the software, the delivery system that produces it, and the data and identities the software handles. Draw the lifecycle from left to right. Product requirements and threat models shape the design. Developers write code and tests inside a controlled source repository. The build system resolves dependencies, compiles, scans, tests, packages, and signs an artifact. Deployment policy admits only verified releases. Runtime controls enforce identity, input, data, network, and resource boundaries. Telemetry and incident findings flow back into design and engineering. The important idea is continuity. A scanner at the end cannot repair an insecure architecture, an overpowered account, or a missing authorization rule. AppSec combines prevention, verification, and detection at the point where each control has useful context. This guide uses the current OWASP Top 10 2025 as an awareness map. OWASP itself recommends deeper, verifiable standards such as ASVS for comprehensive requirements. The top 10 is a starting point, not a claim of complete coverage. Threat modeling makes security part of design. Begin with the system's assets: credentials, personal data, financial actions, administrative functions, intellectual property, availability, and audit evidence. Draw components and data flows. Mark every place trust changes: browser to edge, application to API, service to service, workload to database, build system to registry, and operator to administration plane. Identify identities, protocols, storage, secrets, and external dependencies. Now ask how each security objective can fail. Can one tenant access another tenant's object? Can a user trigger an administrative workflow? Can untrusted input cross into a command, query, template, or deserializer? Can the server fetch an attacker-selected destination? What happens when a dependency, signing key, or identity provider is unavailable or compromised? Convert the important abuse paths into concrete requirements: server-side authorization on every object action, approved cryptography, deny by default network egress, bounded resource use, safe failure behavior, auditable administrative actions, and recovery procedures. Assign an owner and verification method. Revisit the model when architecture, data classification, trust, or exposure changes. A threat model is a living engineering artifact, not a one-time diagram. The developer loop should make secure behavior routine. Start with approved frameworks, hardened templates, typed interfaces, safe query APIs, centralized authentication and authorization libraries, output encoding, request limits, and structured logging. Keep credentials and private keys out of source, examples, tests, images, and build logs. Use short-lived workload identity or a managed secret store. Pre-commit checks can catch obvious secrets and risky patterns, but they're guardrails, not the only boundary. Code review should follow the data and authorization paths. Where does input enter? How is it parsed and normalized? Which identity is active? Which resource is requested? Where is access enforced? What sensitive result leaves the system? Review generated configuration, infrastructure code, migrations, and dependency changes alongside application code. Use unit and integration tests for access control matrices, tenant isolation, validation, error behavior, rate limits, and security headers. Include negative cases: the wrong user, wrong role, wrong tenant, malformed input, expired session, missing dependency, and duplicate request. Static analysis and software composition analysis provide fast feedback, but tune them with owners, suppressions that expire, and secure examples developers can apply immediately. Whiteboard the delivery pipeline as a trust system. A protected branch accepts reviewed changes. An isolated build runner uses a minimal, pinned toolchain and short-lived credentials. It restores only approved dependencies, runs tests and security checks, produces an artifact, records provenance, and signs the result. Security stages can include secret scanning, static analysis, dependency and license review, infrastructure and container checks, unit and integration tests, dynamic testing in an isolated environment, and policy validation. No single scanner covers every AppSec risk. Make gates proportional. Block verified critical risk, expose secrets, failed security tests, unapproved dependencies, invalid signatures, and missing provenance. Route uncertain findings to accountable review. Raw alert count is a poor policy because it encourages noise and bypass. Separate build and deployment authority. The deployment system should verify artifact digest, signature, provenance, environment policy, and approval before release. Promote the same immutable artifact across environments. Do not rebuild production from changing inputs. Protect pipeline definitions, runners, caches, registries, signing keys, and release roles as production systems. Log who changed the pipeline, which inputs were used, which controls ran, what was waived, and exactly what reached each environment. Software supply chain security begins before package download. Minimize dependencies, use trusted sources, pin versions and hashes where practical, review maintainership and update signals, and prevent unreviewed package names from entering builds. Generate a software bill of materials for each release. An SBOM supports inventory and incident scoping, but it does not prove that components are safe or that the artifact was built honestly. Pair inventory with vulnerability intelligence, reachability and exposure context, provenance, signature verification, and remediation ownership. Build from declared inputs in isolated, reproducible environments. Restrict outbound network access. Use separate identities for source, build, signing, registry, and deployment. Avoid long-lived secrets on shared runners. Protect caches against cross-project poisoning. Sign artifacts through a controlled service and verify signatures at promotion and deployment. Preserve source revision, dependency lock state, build platform, test results, waivers, digest, signer, and destination. When a new component vulnerability appears, ask, which releases contain it? Is the vulnerable behavior reachable? Which environments expose it? And what compensating controls exist? Patch or replace promptly according to risk. Never let not exploitable become an ownerless permanent exception. The OWASP Top 10 2025 starts with broken access control. Enforce authorization server-side for every object and action. Deny by default, scope queries to the active tenant, protect administrative paths, and test the full subject resource action matrix. Security misconfiguration includes unsafe defaults, unnecessary features, exposed diagnostics, permissive cross-origin rules, missing headers, verbose errors, and inconsistent environments. Use hardened templates, configuration as code, drift detection, and production-safe error handling. Software supply chain failures cover vulnerable or untrusted dependencies and compromised build or distribution paths. Inventory components, verify sources and provenance, isolate builds, sign releases, and maintain rapid remediation. Cryptographic failures expose sensitive data through missing, obsolete, or incorrectly applied protection. Classify data, use approved libraries and algorithms, validate certificates, manage keys separately, encrypt appropriate data in transit and at rest, and design rotation. Injection occurs when untrusted data is interpreted as commands, queries, templates, expressions, or code. Preserve data code separation with parameterized APIs, strict parsing, contextual output encoding, safe templates, and least privileged execution. Input validation is useful, but it does not replace safe interpreters and authorization. Insecure design means required controls are absent or the trust model is wrong. Use threat modeling, secure patterns, abuse cases, tenant boundaries, transaction limits, and defense in depth before code. Authentication failures include weak proof, session handling, enrollment, recovery, and credential protection. Prefer phishing-resistant authentication, protect reset flows, rotate sessions after privilege change, set secure cookie attributes, and revoke sessions after compromise. Software or data integrity failures happen when code, updates, serialized data, or pipeline inputs are trusted without verification. Validate signatures and provenance, restrict deserialization, protect update channels, and treat build configuration as code. Security logging and alerting failures leave defenders unable to detect or reconstruct abuse. Record authentication, authorization, administrative, validation, and high-value business events with timestamps and correlation identifiers. Never log passwords, private keys, or reusable session secrets. Test alerts and retention. Mishandling of exceptional conditions is new in the 2025 list. Define safe behavior for timeouts, partial failures, retries, resource exhaustion, invalid state, and dependency outages. Fail closed for security decisions, bound retries and resources, make sensitive operations idempotent, avoid leaking internals, and make failures observable. Production is where design assumptions meet real behavior. Apply layered controls at the edge, application, API, identity, service, data, and infrastructure boundaries. Use transport protection, request and body limits, rate controls, bot and abuse defenses, strict routing, secure headers, server-side authorization, schema validation, least privileged service identities, network segmentation, encrypted data stores, and protected administrative planes. A web application firewall can reduce some attack traffic, but it cannot repair broken object authorization, unsafe business logic, or an insecure workflow. Runtime protection complements secure design and code, it does not replace them. Build telemetry around security-relevant outcomes, denied object access, privilege changes, unusual data volume, repeated validation failures, new administrative actions, integrity verification failure, pipeline bypass, dependency risk, exceptional condition spikes, and disabled controls. Connect alerts to a runbook with evidence, severity, ownership, containment options, and validation. Preserve logs and release provenance during investigation. Roll back or disable features safely, revoke affected identities and secrets, patch the root cause, add regression tests, and update the threat model. Measure time to remediate and recurrence, not merely how many findings a scanner produced. Finish with the checklist. 1. Inventory applications, APIs, repositories, pipelines, dependencies, data, owners, and exposure. 2. Threat model important flows and convert abuse cases into testable requirements. 3. Use secure frameworks, centralized controls, secrets management, and least privileged identities. 4. Protect branches, reviews, runners, caches, registries, signing, and deployment roles. 5. Combine code review, security tests, secret scanning, static, dependency, infrastructure, container, and dynamic analysis with accountable triage. 6. Build once, record provenance, generate an SBOM, sign the artifact, verify it, and promote the same immutable bytes. 7. Test server-side authorization, tenant isolation, input handling, authentication, sessions, error behavior, rate limits, and recovery. 8. Map the OWASP Top 10 2025 to deeper verifiable requirements, not scanner marketing. 9. Centralize useful application, identity, pipeline, and data access telemetry, test detections, and incident procedures. 10. Patch root causes, add regression tests, update threat models, expire waivers, and measure remediation and recurrence. Common pitfalls are scanning only at release, blocking on noisy counts, trusting signed artifacts without verifying identity and provenance, logging secrets, rebuilding production, treating a WF as a repair, and claiming complete OWASP coverage from one tool. This is original CipherVibe educational content. Copyright 2026 CipherVibe. All rights reserved.